Hello, everyone. My name is Sushil and I'm a master's student at University of Hamburg. Today, I'm going to present our work on DBLP-QuAD, a question answering dataset for the DBLP Scholarly Knowledge Graph. This is the general outline of our presentation, and I'm going to start with the introduction. First of all, what is KGQA? So KGQA is a task to learning to answer natural language questions using knowledge graph. So given a question in natural language, the task is to find the answer from in a knowledge graph. Knowledge graph is a network of entities and the relationships that form between these entities. Some examples of large public knowledge graphs are Wikidata, Wikipedia, and Freebase. One of the ways to store information in a knowledge graph is using RDF triples. RDF triple forms a subject predicate object format as shown in the example here. Another key component of KGQA is KGQA dataset. KGQA datasets are pairs of questions and logical forms. This logical form can be lambda calculus or Sparkle, which can be executed against a knowledge graph to extract the answers. The dataset might also sometimes contain the answers themselves instead of the logical forms. Here's an example of a question in natural language and the corresponding Sparkle query for the given question. One of the characteristics of KGQA is that the KGQA is dependent on the knowledge graph it was developed for. So a KGQA system developed for Wikipedia, for example, cannot be used for Wikidata. These are the steps followed in KGQA. The first step is entity and relation linking. So given a text or a question, as I'm shown in the example here, the task is to associate the mentioned text with the representation of some real-world entity or relation in a knowledge graph. So for example, the text Villanova Anna here is associated with the entity Anna Villanova in the DBLP knowledge graph. The next step is identifying operators. This includes identifying operators and special functions such as select, ask, count. This is in particular to the Sparkle queries. The third step is query building. Here, given after identifying the entities and relations and then identifying the operators, we formulate them into a valid logical form. This Sparkle or this logical form should be able to generate answers from when executed against the knowledge graph. In which regards to this, there are different approaches that can be used. Those include classification, ranking, and translation-based approaches. However, nowadays, entity and relation linking, although are performed separately, however, step 2 and step 3 are often performed in an end-to-end fashion. Next, the motivation. So most KGQA systems that exist that are built for knowledge graphs that contain world facts. These knowledge graphs include Wikidata, Wikipedia, and Freebase, and the corresponding data sets are QA, LD, ECIR, and Mintaka, for example. And these knowledge graphs and knowledge KGQA data sets only focus on world facts and general information. So if we want to develop a specific KGQA system for a specific domain, for example, the scholarly domain, we require a scholarly knowledge graph and a different scholarly data set for this knowledge graph. So the main motivation in our work is to develop a large KGQA data set for the DBLP scholarly knowledge graph. What is a scholarly knowledge graph? A scholarly knowledge graph is a specific class of knowledge graph that contains bibliographic information. A few examples are DBLP, ORKG, Microsoft Academic Graph, and OpenAlex. Here we particularly focus on DBLP. DBLP is a computer science bibliography service, which includes bibliographic information about major CS journals, computer science journals, and proceedings. The DBLP is present in an XML format, and it forms a publication person entity graph as shown in the figure here. Recently, DBLP released the RDF graph, which consists of about 3 million researchers, 6 million publications, and about more than 250 million RDF triples. And as a result, we ended up using DBLP to develop our KGQA dataset. Next, we discussed the dataset generation process itself. here, this figure shows the overall process, which starts with the DBLP knowledge graph and generating a subgraph. We augment the values and literals in the subgraph. Then we select a template that's from the set of templates. And then we instantiate the template using the augmented values to form the data instance. We look into each step in detail next. First of all, we create a set of template tuples. These template tuples consists of 98 template tuples, which are grouped under 10 different query types. Here is an example of a template tuple. It consists of a Sparkle template, which consists of the placeholders. For example, question mark C1 here represents a placeholder for the entity IRI to be replaced. Similarly, it consists of a list of question strings. Here, this question templates also contain placeholders instead of the actual entity representation. These templates are grouped under 10 different query types, and these are the query types. So first of all is the single fact. Single fact are questions that require only a single triple. Multiple facts require 1, 2, or more triples to be answered. A Boolean asks a true or false question. A negation is adds the not keyword and negates the Boolean. You have double negation, which is an artificial category which adds the negation twice. We have another category called count, where it counts the number of triples. Similarly, we have superlative and comparative, where it compares either two different entities, or it also uses keywords such as most and least. We have union category, which combines the results of two different queries. We have double intent, which asks for two different information, such as in which venue and when. We have disambiguation queries, which only uses partial names of the authors and partial phrases of the title, and the task is to distinguish the particular author from the question itself. Next, now that we have the templates, the next part of the data generation process is the subgraph generation. So here we randomly sample a publication entity, and then we expand the corresponding entity nodes to form a two-hub subgraph as shown in the figure here. And for each data instance, we sample two subgraphs. Now that we have the subgraph and we sample a template from the set of template tuples, now we instantiate the templates to form the data instance. So we replace the placeholders with the entity IRIs and literals extracted from the subgraph. In addition, we also perform some augmentation for the names, where we generate different variations of the same name. We also use either the short form or the full form of the venues. There are also temporal questions in the data set, and for which we use either the numeric or the textual representation for duration. For affiliation, we either use only the university name or the full address of the institution. For disambiguation queries, we only use partial parts of the title, so for which we use Spaces Matcher API to extract the noun phrases. So using these augmented data, we instantiate the question templates as shown here, and using the entity IRS and literals, we instantiate the Sparkle templates as shown here to form the data instance. Here is an example of a fully formulated data instance. So we have the question, a natural question. We have a paraphrase of the question. And then we have a template with the entity IRIs filled in. We also maintain a list of the entities, and we also maintain a list of the relations used in the Sparkle. This can be useful for entity linking and relation linking as well. So with this data generation process, we generate 10,000 questions. And in addition, we also store answers extracted from the DBLP knowledge graph. During the data generation process, out of the 98 template tuples, we withheld 20 template tuples and 2 questions when generating the train set. The main reason to do this is to introduce the generalization challenge in our data set. So we introduced 3 levels of generalization in our data set. First is the ID generalization, in which all the relation classes and logical form constructs that are seen in the train set are also seen in the test and valid set. For compositional, only the relation and classes observed in the train set are seen in the test and valid set, but not the exact specific composition or not the exact specific Sparkle template is seen in the test and valid set. Similarly, in zero sort, either one of relations, classes, or logical form are seen in the test and valid set that are seen in the train set, but not the entire Sparkle template is seen. So with these three levels of generalization, we have the distribution of data shown here, with the majority being ID level generalization, and there are also compositional and zero shot varieties. Moving on to some more statistics out of the data set. So from the DBLP knowledge graph, out of 6 million entities, we cover about 13,000 entities and 11 predicates. And for each query type that we discussed earlier, we have 1,000 questions each. And out of these questions, 2,300 questions are also temporal questions. Also, we do a comparison analysis with other data sets regarding the linguistic variation between the paraphrases used in the data set. And we calculated the edit distance, which is quite comparable to the ECIR-QuAD and significantly higher than the cron questions. We also do this Jacquard similarity and for unigram and bigram, which is significantly lower than cron questions, for example, and comparable to ECIR-QuAD data set. Further, with the baseline, now we also with the generation of the data set, we now move on to a baseline. So for the baseline, we fine-tune the T5 model. We follow Banerjee et al., and where we fine-tune the T5 on the DBLP-QuAD data set. So for fine-tuning, we formulate our input as shown here, where we concatenate each input string with a command parse text to Sparkle query, and then we have the question in natural form. And then we also have the entity linked already, and also the relations are linked. So here we assume that the entity and relation linking is performed beforehand, and it's 100% accurate. And for the output of the T5, we formulate the output as shown here. So we perform experiments with two different variations of T5, T5 small and T5 base. We use these hyperparameters from here, and the scores achieved here are shown here. So for exact match accuracy, as you can see, unsurprisingly, T5 base performs quite better than T5 small, achieving 86 F1 score over 72 F1 score for the T5 small. Note that here we are assuming entity linking and relation linking are 100% correct and are performed beforehand. If these are to be performed from scratch as well, the score line would definitely see some setbacks. So in conclusion, we do have some limitations of our data set. The first is the user information need. So the questions templates that were designed were written by only two people, including two people being the authors themselves. So the questions used in the template might not best reflect the user information need. However, we do introduce augmenting the entity surface forms and literal forms to best represent the different ways users write these information and questions. And next, we also have 80% questions. We also have a problem of test leakage to a certain extent, in that 80% of questions in the test set were formulated using the templates used in the train set. So however, to counteract this, we do withheld 20% of the templates, and also we withheld 2 question templates in the generation of the test set, so that the questions found in the test set and valid set are totally unique to and not seen in the train set. Next, for publication titles, we usually users do not write the full publication titles. However, this is what we have done in our KGQA dataset. This is definitely an interesting and could be an interesting entity linking problem or challenge that could be tackled in future variations. In addition, some queries that did not produce answers, and we discarded these queries from the data set, although these queries were still valid. And the reason we discarded them was that it did not produce answers, and the reason they did not produce answers were because the information was missing from the data, from the knowledge graph itself. So in conclusion, so we developed a scholarly KGQA dataset for the DBLP knowledge graph. We used an automated process to generate 10,000 questions. And we introduced a very challenging entity linking problem. In addition, we also foster a focus on generalization ability of the language models on the dataset. Further, we released baseline scores with the fine-tuned T5 model for further development of the dataset. Thank you for your attention. If you have any questions, please feel free to contact us. You can also read our paper and visit the slides on these URLs. Thank you.